Yeah. Hello, everyone. I'm Mason, and I'm going to talk about Scroll and the zkEVM that we're building. So there's just so that we're like clear on like what we're building. There are a couple of different types of like zkEVMs, and so the sort of like the top one is like language level. So this means that you take like a higher level language like Solidity or Yule, and you transpile that to a snark-friendly VM, and then that's sort of like what you produce a zero knowledge proof of. And so this is what Matter Labs and Starkware are doing. And then there's a bytecode level zkEVMs, which is what us, Scroll, Hermes, and Consensus are doing. And so in these, you interpret the EVM bytecode directly, and then you can prove, you sort of prove the the bytecodes are executed correctly, like one by one. And so I guess like in our case, like we have like one gadget that proves each, or usually like one gadget that proves each EVM opcode. And then in Hermes' case, they, I believe, have like micro opcodes, and a bunch of these micro opcodes will map to each EVM opcode. And then but there are still certain differences between this and like what happens at like a consensus level zkEVM. One of which is like we use like a different state like hash function, so the state roots are different. Then potentially, like we discussed earlier, like the gas pricing might be different. And then then the final one is a consensus level zkEVMs, and so this one would basically just be a zkEVM zk proof that in fact that sort of like the state root transition is correct according to like the Ethereum L1 consensus. And so this is what like on the roadmap for Ethereum, what is meant by the zk snark everything node. We're building a bytecode level EVM zkEVM. All right, so let's talk about like what we're actually doing. And so Haichen had a diagram that was sort of like that showed the like our workflow, and just to go over it again. So like people have like transactions. We run them on our forked Geth node, and this produces an execution trace. So there's the execution logs, block headers, the transactions themselves, the bytecode for all the contracts that got created, used, and then Merkle proofs for all the storage slots that got touched. And then this gets fed into our zkEVM circuit, like all the circuits that comprise our zkEVM. Those circuits produce a bunch of proofs. All these proofs are then fed to the aggregation circuit. The aggregation circuit produces a proof that all of these proofs are in fact valid, and this like aggregation proof gets sent to the L1 contract, which does all the stuff that Haichen talked about earlier. And then at the same time, the Geth node provides some data to the L1 contract, so that everyone else can figure out like what it is the validity proof is a proof of. Okay, so in my talk, I'm just going to be talking about the stuff that goes into the zkEVM circuits, and then the stuff that comes out of it, so the execution traces, and then the proofs. Okay, so at the very top of our zkEVM is the EVM circuit, and so this constrains the operation of like the EVM state machine. So what happens here is there's things like the amount of gas that you have left in your execution, the like program counter, various call context, block context, constraint variables. Let's see what else is there. So it's sort of just like a lot of the bookkeeping that you do as the EVM sort of like goes like bytecode by level, opcode by opcode. Like executing like the transaction and calls, and so, but then to keep like the engineers I'm one of the engineers at Scroll, and so like to keep us sane, we like break this down into a bunch of other components. And so like the first one is there's a bunch of like zk unfriendly opcodes like catch is one, and then like all the like logical operations like and or, exclusive or, not, what have you. And so these are done by lookups. Well, actually, I mean, everything else is done by lookups too, but these are also done by lookups. And so like in the case of the like logical like and ors or whatever, these are done by like the lookups that Yingtang just described into fixed tables. So right, rather than like write the constraints that show that like, hey, like, you know, A and B is equal to C, we just look it up directly. There's a table that has like every single input to the like every single input to and then the corresponding output, and then because these are fixed, like everyone can just see that in fact like we have filled out this fixed table correctly. And so okay, so yeah, like I'll talk about how that's actually possible later, because like and then so catch has a right, it has like the table that Yingtang just described earlier, right, where there's a table that has like all the pre-images in it along with the catch values in it. Okay, so and then there's also the so I guess like in Yingtang's talk, she called it the state circuit, which is actually what it's called in the code, but I think it's more clear to call it the RAM table. And so this verifies that like the reads and writes aren't actually like that the reads and writes are like have been done like according to like how you'd think they would be done, right? Which is so that like if I write a value to some slot and then I read the like a value from it later, that the value hasn't actually changed. And then let's see. So then there's a bunch of other lookups. So like there's the bytecode lookup, right, which basically proves that in fact the opcodes that the EVM claims it's executing are in fact the opcodes in the contract itself. There's a transaction lookups which verify that the like the call data in the transaction is, you know, the call data in the transactions that we're claiming. And then the block context, which is sort of like, you know, has things like the block number, block hash, timestamp, stuff like that. So all of these are done by lookups. Right, and so this sort of just like is like how our circuits like sort of talk to each other. And then so there's more circuits on top of all of these that can make sure that the values in these tables are actually correct. So for the and or like the logical operation table, right, these are fixed, so we don't need a circuit to prove that these are correct. For the RAM circuit, for the RAM table, like we have a circuit that shows that in fact the values aren't changing in between reads and writes. And then there's also the MPT circuit, which is showing that for initial reads that the values that we're initially reading out of, say, storage slots are can actually be found in the state tree. And so yeah, so there's like various things like the bytecode circuit. And there's like interdependencies between all of these, right? The bytecode circuit actually has to look up catch values. The catch circuit proves that every row in the catch table actually does correspond to the SHA-3. The TX circuit has to look up into the catch circuit table because, right, you have to verify that in fact these transaction hashes are correct. And then additionally, you also have to verify that we have signatures for all of these transactions, because so we can't just like sort of like stuff it full of transactions that we're making up. And then the transaction signatures are themselves verified by the ECDSA circuit. So yeah, so this is sort of how everything depends on each other in the zkEVM circuit. So yeah, if you guys have any questions, feel free to ask. All right.
Oh, yeah, quick question.
Yeah.
So I might not have full context, but the verifier will have access to all of the like raw numbers to look people. Is that right?
No. So well, so I guess like right. So there's the aggregation circuit at the very end, right? So the verifier has like actually access to basically none of these tables other than the and or this one, right? Because this one is fixed. The other ones are assigned. Well, actually, sorry, that's not true. I think some of them are like instance like instance columns, like what Yingtong was saying. So these are public to the prover and verifier. And then so this table is fixed. But then, for example, like the RAM circuit is an advice. These are all advice columns, so the verifier doesn't actually see them. The verifier only gets like a proof that the prover provides that like all the constraints in these different circuits are satisfied.
Right. So would there be like some Merkle type constraints that like to make sure that the bytecode that you're claiming lives here actually is
yes, I believe there should be some more like there should be some more like dotted lines here. I think, yeah, right. For example, like yes, like the bytecode, you need like an NPT lookup to confirm that like these bytecodes that we're claiming are like actually in the state tree.
Right. Like the NPT circuit, I guess, would talk to the.
Yeah. So I think there should be like an NPT table here that consists of sort of like NPT proofs for like sort of all sorts of facts, and then the bytecode circuit would look up into it. To every time it's like saying like, hey, this is the bytecode at this address.
Okay, that makes sense.
Okay. So I guess, yeah, so that's sort of like the high level picture. And then now I'm just going to talk about like sort of like how some of these circuits work. So the EVM circuit, the one at the very top here, is sort of basically looks like we have like one region for every like execution step, I guess, and usually each execution step corresponds to an opcode. And so like in this example, where you can imagine like that the opcodes that we are interested in proving can like the first one's push, and then I add whatever is on the stack, and then I multiply, and so on and so on. And so like to talk about slot I in particular, right? So there are so all of these. So I guess so A1 through AW are sort of all advice columns that the prover assigns, and then QOP basically is a selector column that just says like basically it's one every like however many block. Okay, I mean in this case, right, it's every like 6 rows is one. Right, which just means that like basically every 6 rows I prove the execution of one opcode. And so there's some context variables. So like PC stands for program counter, SP is the stack pointer, gas is how much gas is left, and then there's more. And then there's also these sort of like selectors for each of the opcodes themselves. So there's one for like addition, one for multiplication, one for shift right, and so on. And there's also error states of the VM, EVM, right? It's like I'm out of gas, I've overflowed the stack, whatever. And then there's like these V0 through Vn are sort of operating values, and so these have basically like context dependent values, context dependent names. So like depending on which opcode I'm currently proving, they have different interpretations. And so let's see. Okay, so I guess, but first, like one thing that we should talk about is how do you handle 256-bit words? So the EVM has 256-bit words, which is unfortunate because the field prime that we use is slightly smaller than 256 bits. And so the way we deal with this is, let's say we have like a word A, and then we break A down into its constituent bytes. So there's 32 of them. So right, so A is equal actually equal to this value here, right? So like the least significant byte plus 256 times the second least significant byte, and so on and so on. And then what we do is like actually when we want to like assert the equality of two like EVM words, rather than check that like, you know, if we have like A and B, right, rather than check that A is equal to B, we can't do that directly. So instead we compute this random linear combination of them. And so this is sort of like the random linear combinations that Yingtong mentioned earlier between custom gates, where so you generate this theta according to some public randomness, and then we compute this this sum like a sub RLC, which is instead of using like a0 time like a1 times 256, you just have a1 times theta, and so on and so on. And then this thing mod fp will actually be small enough to fit in the finite field. And so this just means that like when we compute our lookups, we have we just compute the RLC of these values instead of just using the bare values. And so this technique of breaking up the words into bytes also comes up when we're computing things like logical operations on the words, right? So if you want to compute like an like the bitwise AND of A and B, then we just compute the right. You can just do this byte by byte and look up the like the bitwise AND of like A0 and B0 and A1 and B1 and so on and so on. So okay, so let's say we are back to the add opcode. So we also have these opcode selectors, and so the constraints for these selectors are basically like what they're supposed to be is 0 and 1 binary selectors, and exactly one of them is 1, and the one that's 1 is the opcode that we are trying to prove. And so the constraints that we have in this case are right. So like it's basically the selector times 1 minus selector is 0, which means that each selector is either 0 or 1, and then the sum of them is 1, which means that exactly one of them has to be 1. So this sum here can't overflow because there's not enough terms in this. There's not enough terms in this sum to overflow. And then, so in the case of addition, right, we prove it byte by byte in the way that you do addition, like with like in base 10 on a whiteboard, right? So this first constraint, right, says that the first byte plus the second byte of the first byte of A plus the first byte of B is equal to the first byte of C plus potentially the carry bit times 256. And then this thing gets repeated for all 32 bytes. And then we are missing constraints here that say that in fact the carry bits are 0 or 1. And then, right, but then if all these constraints hold, then the claim will, like, then it will hold that, right, the value represented by the bytes of C is actually equal to like A plus B. Okay, and then, so then there's sort of like EVM bookkeeping to do, right? So, right, the program counter here has advanced by 1 because now we've successfully proven the addition opcode. The stack pointer has gone down by 1 because the addition opcode pops 2 values off the stack and then pushes their sum onto it. And then the the gas has gone down by 3. All right, because that's the gas cost of the addition opcode. And then there's also more, right? Like we have to check that the stack pointer is still less than 1020, still less than 1024, and things like that. Any questions so far? Or, oh yeah.
Yeah, I had a question about the random linear combination.
Yeah.
And so, is there some way to? I guess where does the randomness come from? Do you need to do an extra step in trusted setup to get like?
So I think the randomness would be like basically some hash of like the public inputs that you pick. But yeah, like you have to be careful about it, because if like
a hash of the transcript so far or something.
Yeah, right. But yeah, like you can't just insert any value for theta in there. And then there's like a lot of like carefulness you have to do, right? You have to actually make sure that none of the values that you're randomly like combining are like themselves random linear combinations, because then there like issues come up there too. Sorry, you also had a question, or?
Yeah, I was like maybe a naive question, but
no, it's fine.
like what's preventing you from picking a bigger prime and avoiding like having to do this random linear combination?
Sorry.
So you said the reason you have to do
Yeah.
this random linear
Oh,
thing,
yes,
right,
yes.
is the prime is just
Right. So if the prime were larger than 2 to the 256, then this is like actually like a hardware problem for us, right? Because we have to
Okay, yeah.
you have to multiply these larger primes. Now they don't fit into 256 bits. So now like
Gotcha.
yeah. Okay, let's see. Okay, so and then okay, so now we like in our EVM circuit we have like C, which is equal to A plus B, but then all of this sort of needs to be like communicated with like the RAM is communicated with the RAM table. And basically what happens here is that, right, like when we pop the A from the stack, what actually happens is that the EVM circuit says like this lookup, this row exists in the RAM table, and then so I think this value corresponds to VB, right? So I'm saying that at position 1023 I got VA, at position 1022 I got VB, and then this push goes back to position 1022. And then so the EVM circuit, all it's really doing in this case, right, is constraining that VC is equal to VA plus VB. So which brings me to the RAM table, or actually, no, it doesn't. Okay, so then we so far I've all just been talking about the constraints themselves. So the other part of generating the proof is you have to fill in the witness. You have to actually fill in the witness from the geth traces that we have. And so this is, I mean, there's just like a lot of like sort of like data processing to do here, right? Where like the geth traces come to us in like a JSON form, and then we have to process them so that now there are these like Rust structs, and we fill in the context, right? So like geth I believe just tells us like here's a program counter, here's a stack pointer, here's the gas, right? But then some like these things, right, don't have a corresponding geth value, so we just have to like compute them ourselves, right? But this is just like, okay, like put 1 where for the opcode that we're executing right now, and then 0 for everything else. And then, right, so then we also have to fill in like the intermediate values that were used to prove that in fact VA plus VB equals VC. So like here are all the bytes of VA, here are all the bytes of VC, here are all the carry bits, here are all the bytes of VC. Okay, so I think like Halo 2 like in the main branch right now only lets you look up from fixed tables, but we have we've like modified it so that you can now look up the lookup argument actually works for like into advice columns as well. And so this is very important for us because right, like a lot of our lookups are not fixed, right? Like the RAM table changes every time for every new transaction, so it does it. Yeah, so it wouldn't work if they had to be fixed. And so the RAM circuit is the thing that constrains the RAM table. And so right, so earlier when we're executing the VM or the EVM, you sort of like these are random access, right? So you might read from the stack, and then you read from the memory, then you write to the stack, and then you read from the storage, and then so on and so on, right? And so, but what we need to prove is that like if I write to the stack and then I read from the stack, then that value doesn't change in between. And so, but like the order of the reads and writes in the EVM circuit aren't conducive to proving this. So the RAM circuit basically has the same contents as the RAM circuit proves this, and the way it proves it is it sorts the reads and writes in a different order. So instead of them being in execution order, in this case, right, it sorts them so that all the stack read writes come first, then all the memories, and then all the storage reads and writes. And then within the stack reads and writes, we sort them additionally by the address and things like the call ID, so that we can verify that within a call ID, within like we have read-write consistency like for every particular stack address. So let's see. So yeah, so like in this case, right, so this read-write index sort of tells you how the EVM, I guess, yeah, like how the EVM like access, like in what order the EVM accessed these elements. But then in the RAM circuit, right, the RAM circuit constrains that these things appear in this sorted order, and right, and then now like we can basically write these simple constraints that say like if it's a read, then the values don't change, and if it's a write, then the value can be whatever you want it to be. And then additionally, you also have to add constraints, right, saying that, right, for like an initial read to a stack should be 0, an initial read to a memory should also be 0, and an initial read to a storage should be like whatever the MPT circuit says it is, right? And so that's also a constraint that has to show up in the RAM circuit. Yeah.
Did you say this sorted by address?
Yes.
And what's the reason for that?
Well, because like you want all the reads and writes to a particular address to be like one after another, right? Because it's like what Yintong was saying earlier, like you can't okay, like it's like you don't want to have these like long distance constraints, right? Where like, oh, I'm like, you actually can't even express it in Halo 2. Like you can't say like, oh, like I read it here, right, and then like 10 rows later, or like maybe 100 rows later, depending on like what's happening in the EVM, right? Like I read from it, and then I want these two values have to be the same, right? So if they're sorted, then like it's actually just like the next one.
It's sorted by address, but also it's sorted temporally for each address.
Yeah. So it's the sort order is like the tag, the address, and then the read-write index. This is actually a simplified version of it. There's like even more things because there's other things that are effectively like random access, like different call context variables are in this transaction log, logs, like even things like oh, like here are the like accounts that I've accessed in this transaction, and so all of these are in the RAM circuit, but they're not on the slide for simplicity. Okay, anything else? Okay, so yeah, so these right, so then sort of just these are just some of the constraints in the RAM circuit, right? So that if it's a read, then the value has to equal the previous value, i.e. it can't change, and then we also have to check that that these values are valid, right? So RW is 0 or 1. The tag is one of stack, memory, or storage. So like, these correspond to like just 1, 2, 3, and that in the case of the stack, right, the address has to be within 1024. And then so yeah, this is like what I was talking about earlier, like this constraining the sort order of the keys, right? So basically, first they're sorted by tag, then they're sorted by address, and then they're sorted by read-write index. And there's actually a final constraint that like you can't repeat a read-write index either. All right, so yeah, just want to thank all the community members who have helped us write this code. And are continuing to help us write this code. So yeah, are there any questions? Any more questions? Oh, yeah?
Yeah. Sorry, could you explain a little bit what the advantages are of going for bytecode equivalents rather than the transpiling version?
Well, I guess. Okay, so I guess like one is just like there's some like implementation things that are like easier because you can. I guess like sort of like what kind of advantages are you interested in, or like because like there are trade-offs, of course, right?
Yeah, I was just thinking that since like presumably as far as portability, like people generally have their source code in Solidity or whatever, and so like those should be equally the same. So like, are there implementation things that are easier? Are there like nuances that the other version, the transpiled version, doesn't support?
I think I'll defer to Haichen.
Okay, yeah. So I think one important implication is like with another set of the toolchain. So they reuse a lot of things like that, bringing data into system, and you can reuse a lot of all of things. You don't need to install extra plugins or like another compilers, and also extra compiler like infrastructures could be like adding more security concerns, like if there's anything like the we need to trust another compiler that's built by another team. So we kind of like the whole like, so we need compilers and all of the infrastructure to build upon that. So we like, probably need some extra modifications into the video workflow. So that by keeping this bytecode compatibility, so we can maintain the fast developer experience for like the holidays and so they do.
Oh yeah, Remco?
Is that also, do you also need the bytecode compatibility to implement and create opcode? Or is it something you can uniquely do if you go down this route?
Well, yeah, like I mean, yes, I guess yeah, like in the case of like create, right? Like there you would need to. I mean, like yeah, like, I think like you could work around that, right? But yeah, like with bytecode compatibility, you don't have to worry about it.